Okay, so hello everyone. So today our speaker is Giacomo Mastella, who's joining us from Rome. So Giacomo got his bachelor's in geological science from the University of Ferrara in 2018, where for his project he did an interpretation of seismic profiles for the reconstruction of a 3D geological model of the subsurface of Ferrara. He then moved to Rome to get his master's from the University of Roma Tre in geodynamics and volcanology. And he's now a PhD student at the University of Roma Tre, investigating the megathrust seismic cycle. So Giacomo's interests are in like megathrust earthquakes and specifically using analog models and machine learning to investigate how the megathrust seismic cycle works. So yeah, very lucky to have you today, and take it away.
Okay, thank you so much, Edward, for the nice presentation and for inviting me. And it's a pleasure for me being here. So today I'm gonna show you some results from the first 2 years of my PhD. And especially I'm gonna talk about the megathrust seismic cycle and about some spatiotemporal deep learning techniques that we have mainly applied to some laboratory data obtained with the seismotectonic analog models. But we are gonna talk also about some applications of deep learning with the natural data. And before starting, I would like to thank Francesca Funicello and Fabio Corbi, who are the two main supervisor of my PhD project, but I would like also to thank Jonathan Bedford, Matthias Rosenau from the Ruhr University of Bochum and the GIZ of Potsdam, who are helping me and who helped me in in doing some of the stuff that I'm going to show you. So the talk is going to be divided mainly in two parts, let's say 3 parts. And during the first part, I'm going to introduce you a novel seismotectonic analog model of the megathrust seismic cycle that we have developed at Experimental Tectonics Laboratory at the Roma Tre University. And I'm going to show you some experimental results that we obtained. Then I'm going to talk about some deep learning applications that we apply to laboratory data in order to forecast laboratory earthquakes. And last but not least, I'm gonna talk about what actually I'm doing right now and what I would like to do during the next year about the application of the deep learning techniques we applied in the laboratory with real data from natural subduction zones. So let's start defining what is the megathrust. So as probably you already knew, the megathrust is defined as the frictional interface between overriding and subducting plate at convergent margins. And within the megathrust shear zones, mega earthquakes are generated, which are earthquakes with a magnitude higher than 8.5, which are one of the most devastating expression of the Earth's dynamic. Unfortunately, due to the paucity of direct observations from the natural prototype, as well as to the limited resolution and completeness of paleoseismic archives, there are still a lot of aspects of the megathrust seismic cycle that we don't know. In this context, seismotectonic analog model offers us a useful tool to overcome, for example, the paucity of direct observation from natural systems. And a seismotectonic analog model is simply a reproduction of a given geodynamical system at more convenient spatial and temporal scales. So when we are working with a seismotectonic analog model, we are working with a model that is not composed by natural materials, not by natural rocks, but by analog materials. Analog materials are materials that can in some way reproduce the first order characteristics of the natural materials in a downscale fashion. They are materials that are scaled, for example, in terms of rheological, frictional, and geometrical properties. The first seismotectonic analog model of the megathrust seismic cycle has been devised by Matthias Rosenau at the GIZ in 2009. And this kind of modeling technique has several advantages. First of all, it reproduces this kind of modeling technique, reproduces the process of the seismic cycle at laboratory scale. So the long-term steady state accumulation characteristic of interseismic stages and the rapid stretch drops characteristic of the coseismic stages. And second, the frictional behavior of seismotectonic megathrust model can be described in the context of the rate and state framework, which is the empirical framework generally assumed to model the frictional behavior of natural faults. But probably the most important advantage of this kind of modeling technique lies in the fact that they can reproduce a lot of seismic cycles in only a few tenths of minutes of an experimental model, which means that we can have access to a very long catalog of analog megathrust earthquakes in the laboratory. In particular, during my PhD, we developed a novel and innovative seismotectonic model that we have called FOAMQUAKE. The name FOAMQUAKE, which is a bit strange, let's say, it derives from the fact that the model is composed by a foam rubber wedge, which overlies a 10 degrees dipping rigid plate. This foam rubber wedge tries to mimic the elastic behavior of the upper crust at convergent margins. Within the rigid plate, there's a conveyor belt, which is driven by a stepping motor, mimicking a steady-state subduction process. And at the contact between the foam rubber wedge and this conveyor belt, in this surface, along this surface that we have called the analog megathrust, we placed two different materials in order to reproduce the heterogeneous frictional configuration of real megathrust. And especially we place a 1 centimeter thick layer of rice surrounded all around by the sand. Why did we use the rice and the sand as analog materials? Because the rice, in the context of rate and state framework, is a velocity weakening material, which means that within the rice we can nucleate frictional instabilities. While all around the sand instead is a velocity neutral material, which means that within the sand, no frictional instabilities can nucleate. So what it occurs in the model is that due to a continuous kinematic loading at the wedge base, FOAMQUAKE experiences quasi-periodic cycles of stress accumulation and rapid stress drops through the spontaneous nucleation of frictional instabilities. The experimental model is monitored thanks to an high-resolution view camera, which acquires images at a very high frame rate. And thanks to the application of particle image velocimeter techniques, computing the cross-correlation between consecutive images, with our monitoring technique, we can reconstruct the surface velocity field measured within the model surface. And especially, we can discretize the surface velocity field in a grid located above the model surface, where each point of this equally spaced grid is the analog of a GPS station at the natural prototype. So here an analogy between our monitoring system and a geodetic network and natural subduction zones. So let's go to some results. So in this slide, there's an example of the FOAMQUAKE seismic behavior. And especially this here, I represented the results obtained with an experimental model characterized by the presence of only one rise asperity, and above this asperity, there's a normal load of 40 Pascal. So it's an experimental model with a duration of around 2 minutes. And in 2 minutes, generally FOAMQUAKE experiences something like 100 of events. So the mean recurrence time of frictional instabilities generated by FOAMQUAKE is of the order of 1 second. So here each peak simply represents one analog earthquake. If we represent the line time model evolution, where here each thick vertical line represents the trench parallel extent of a given analog rupture, we can see that there's a sort of variability in terms of rupture areas. So for example, there are some ruptures, such as this one, that are very small, while other ruptures involve instead all the model dimension along trench. The first subplot here depicts four random, the interseismic cumulative displacement observed for 4 random seismic cycles. And especially I represented the locking And we can see, and I represented the surface motion, the cumulative surface motion, thanks to these red arrows. And as you can see, during interseismic cycles, the motion is landward directed. So this line here represents the trench, and all the vectors are directed to the bottom of the slide, so landward. This motion is completely inverted during coseismic stages instead, during which instead all the motion is trenchward directed due to the so-called elastic rebound process. In particular, we investigated the source parameter scalings of the frictional instabilities that we can generate with FOAMQUAKE. And interestingly, we found that analog earthquakes follow a similar source parameter scaling as large interplate earthquakes. So for example, here I represented the relationship between the seismic moment and rupture area, seismic moment average dip, seismic moment asperity area, seismic moment versus duration of analog earthquakes. And the best fitting lines for analog earthquakes are here depicted by the red lines, while the blue lines represent the best fitting lines obtained by Murotani 2013 for natural interplate earthquakes. And we can see that the slope of the best regression lines for the analog earthquakes follow a similar slope with respect to the Murotani scaling laws. So we found a sort of similar scaling between what we can generate in the laboratory and natural earthquakes. Especially given that FOAMQUAKE is three-dimensional, this gives us the opportunity to perform some experiment characterized by the presence of more than one asperity. So especially, we played a little bit trying to complicate the heterogeneous frictional configuration of the megathrust, placing two asperities divided by a barrier. And we varied even the normal load above the two asperities. So here I perform 4 additional experiments, keeping constant the load above one asperity that I call the reference asperity, while I changed the load above another asperity that I call the secondary asperity. When you run some experiments with a configuration characterized by the presence of two asperities, the space-time rupture behaviors generated by the model became more complicated. So here you can see the line time model evolution of 5 seconds from an experiment characterized by the presence of two asperities with the same load above them. And we can see that there's a coexistence of full and partial rupture, namely ruptures during which, in one case, only one asperity fails coseismically, so a single asperity rupture, such as this event, and other events, such as the event 31, during instead both the two asperity fail coseismically almost together. And especially considering this event, we can clearly see a rupture cascade process, which is simply a process that leads to, let's say, a triggering between two asperities. So here, for example, I represented an analogy, a comparison between the space-time rupture propagation observed for the Pedernales earthquake, a megathrust earthquake that struck the Ecuadorian margin in 2016, and with the propagation observed from an analog earthquake generated by FOAMQUAKE. So we can see that during the Pedernales earthquake, interestingly, the rupture started within an asperity located to the north. And then, as the time increases from the onset of the event, the ruptures propagate to the south, triggering to fail another asperity. A similar pattern it's observed here to the right and can be reproduced by our FOAMQUAKE experiment. So we can see here that the rupture starts within one asperity, and then in a later moment, the other asperity is triggered to fail. So we can say that our model can reproduce the so-called rupture cascade process. Interestingly, we analyze even the number of double asperity ruptures as a function of the difference of the load above the asperities. So here what I represented is the number of analog earthquakes in an histogram as a function of the difference of load above the two asperities. And the color depicts the different typologies of analog earthquakes. So in orange, for example, we have double asperity ruptures, so ruptures during which both the two asperities fail co-seismically together. And we can see that the number of double asperity ruptures decreases as you increase the difference in terms of normal load. And this is because the normal load controls the frictional strength of one asperity. And if the normal load above the two asperities is very similar, the two asperities tend to behave systematically in a synchronized manner. While if you change the normal load above one asperity, then the shear strength of this asperity changes, and the two asperities tend to work instead in a separate manner. So all of these things that I show you, all of this observation, demonstrate that FOAMQUAKE can reproduce what is called the superimposed cycles behavior of natural subduction zones, which is a behavior that includes all the observations that I show you so far. And especially, I suggest you, if you are interested in understanding better what a superimposed cycle behavior means, I suggest you to read this nice paper from Philipp Bosian and Meltner. And especially if you are even interested in what I show you so far, we published recently a paper on JGR about these experimental results, so you can check out this article. So basically, I hope that I convince you that FOAMQUAKE can reproduce all of the key features of the megathrust seismic cycle in appropriate scale fashion. But the most important thing that I would like to underline is something that I already told you, which is the fact that FOAMQUAKE can reproduce a lot of seismic cycles in only a few tens of minutes. And this peculiarity of FOAMQUAKE makes this experiment as an ideal tool to test new prediction strategies in the context of laboratory earthquake prediction. So let's go to the second part of the talk, which is instead dedicated to some deep learning applications with laboratory data. So in the last few years, machine learning has completely revolutionized our way of thinking about laboratory earthquake prediction, but I will say even about our idea of predicting natural earthquakes. The machine learning has been applied, for example, in double direct shear experiments, where it has shed light on several aspects of the physics of laboratory failures. And it has been applied even in seismotectonic megathrust analog models, where it has provided new implications for the monitoring of subduction systems. However, the previous machine learning methods applied in these two different kinds of experiments were limited by some concerns. And especially regarding double direct shear experiments, the main concern regards the fact that generally no spatial information can be taken into account in this kind of experiments, because the samples of rocks that are squeezed in this kind of experiments are too small, and so it's very difficult to understand something about the spatiotemporal evolution of the stick slip process, which is modeled. On the contrary, different is the case of seismotectonic megathrust analog models, which are by definition three-dimensional, despite, of course, when we are working with this kind of models, we are not working with real rocks. And so, for example, Corby 2019 has demonstrated that machine learning can be used even to incorporate the spatiotemporal evolution of the stick zip process in this kind of experiments. But the methods that Fabio Corby has applied in this context were limited by two main concerns. And these concerns regard the fact that the previous method need subjective feature extraction and are limited by the need to define a threshold to identify laboratory earthquakes before the application of machine learning. And with feature extraction, what I mean that some features from the monitoring data acquired with the monitoring system used to analyze the experiment. From this kind of data, some statistical features needed to be extracted. And this extraction was a choice of the user who used the machine learning algorithm that potentially could introduce some bias in the results obtained with the machine learning algorithm itself. So to overcome these problems, we decided to devise a novel spatiotemporal forecasting strategy by taking advantage of less arbitrary deep learning-based regression tools. Especially before explaining you how our prediction strategy works, what I would like to underline is that we decided to apply this method with different kind of data acquired with different experiments, especially with not only with FOAMQUAKE, but even with data derived from the GELQUAKE experiment, which is another megathrust analog model where the main difference with respect to FOAMQUAKE lies simply in the fact that the wedge that mimics the behavior of the upper crust is a gelatin wedge. So the two different experiments are characterized by different stray rates and are even characterized by different monitoring systems. And also with FOAMQUAKE, we decided to apply the methods we devised with data derived from different experimental configuration. So both from single asperity models and double asperity models. So here the forecasting strategy we adopted is described. So first of all, we consider one experiment, okay, both from FOAMQUAKE and GELQUAKE, and we divided the input dataset into the training, validation, and testing set as commonly used in machine learning problems. So the artificial intelligence model is trained only using the training set, while the validation set is used to tune the hyperparameters of the artificial intelligence model. And while the testing set is only used to test the ability of the model to generalize with data that it has never seen before. And our method aims especially to forecast surface velocity field based on past experience. And to understand how the method works, we can focalize our attention in this subplot here. So basically, the model works in this way. There's a spatiotemporal input, a sequence of frames in the past, of velocity frames in the past, from the time t minus m to the time t, which is used as an input to train the deep learning model to forecast only one frame in the future, at a time t plus ph, where ph is the prediction horizon. So how far are we predicting the future? So in the context of predictive learning, this is called a many-to-one framing, where you have a sequence of frames in the past and only one output in the future. And it's a method that is self-supervised in a way that there's not the need to define a velocity threshold, and that there's not a need to extract features because the raw velocity field is used as an input to train the deep learning model. And the method allows us to forecast the whole seismic cycle, including interseismic and coseismic stages, and simultaneously to forecast the onset of a laboratory earthquake, its magnitude, and its space-time propagation at different horizons in the future. Which kind of algorithms did we use? We use convolution neural networks and LSTM models. So I'm not entering into the details of these algorithms, but if you're interested, you can ask me whatever you want at the end of the talk. But basically, they're very useful methods, very useful algorithms that are capable to incorporate both the spatial and the temporal evolution of a given process. And we contrast the predictions obtained with these three different algorithms with respect to the predictions obtained with the free forecasting baselines. And why did we use these forecasting baselines? Because generally when you are working in the context of predictive learning, it's very important to justify the application of the methods that you are proposing. So to legitimize here our application of very complicated deep learning algorithms, we decided to contrast the predictions obtained with these algorithms with the prediction obtained with the free baselines. So let's go to some results. So here, what I represented the results from FOAMQUAKE obtained analyzing a FOAMQUAKE experiment characterized by two asperities. And I represented the normalized root mean square error, which is a metric that measures the effectiveness of the model in predicting the velocity field as a function of the prediction horizon and for all the architectures that we tested. And especially I represented the results considering two different prediction scenarios. In the prediction scenario A, we are considering both the interseismic and coseismic frames, while in the prediction scenario B, we are only considering coseismic frames. So we can see that there's not a big difference in terms of prediction abilities when we look to this subplot. So all the models perform similarly, even if there's a substantial difference between deep learning architectures and baselines. But these differences became very clear when instead we focalize our attention only to coseismic frames. And especially we can see that the best prediction algorithm seems to be the one in blue, the convolutional LSTM architecture. So we compare the results even between the two different experiments, FOAMQUAKE and GelQuake, that we tested. So I will not enter into the details of this plot, but the only thing that I would like to underline here is that the errors for FOAMQUAKE is very smaller with respect to the errors calculated with the GelQuake experiment is very smaller with respect to the errors calculated with FOAMQUAKE, which means that the GelQuake experiment is easier to predict. And we also compare the errors calculated for the different experimental configuration that we tested with FOAMQUAKE. So here I represented the errors again as a function of the prediction horizon for the three different configurations that we tested with FOAMQUAKE: a double asperity model with a different normal load, a double asperity experiment with an equal normal load above the two asperities, and a single asperity model. And especially in this case, you can see that the experiment characterized by the lowest error is the double asperity model with a different load above the asperities. And this is simply due to the fact that the load controls the level of noise of the interseismic deformation. And so given that in this case, in this experiment, the one with the different load, you have the largest load above the asperities, this makes the prediction easier to be obtained. Instead, if we concentrate our attention into the coseismic frames, we can see that the easiest experiment to predict is the experiment characterized by the presence of only one single asperity. This is due to the fact that, of course, if there's only one seismic asperity in the model tends to generate always the same typology of rapture, while if you are working with more than one seismogenic sources, you can have both single and double asperity raptures, so there's a larger variability in terms of rapture areas of analog earthquakes. So, but let's visualize the predictions that we obtain with our deep learning architectures. So here I represented the predictions obtained with the CNN LSTM architecture with a FOAMQUAKE experiment. So let's try to read this plot. So along the x-axis, there's the time, so the frame number. So basically, this is here one analog rapture is represented. You can see, for example, here that the rapture starts in the deeper portion of the analog megathrust, then it triggers to fail one asperity, and then in a later moment, even the other asperity is triggered to fail. It fail, no? And instead, along the y-axis, we have the prediction horizon. So for example, the second row here represents the predictions obtained with a model trained to forecast the velocity field only one frame in advance. So at a prediction horizon of 1, which means, let's make an example, like being at the frame 4019, trying to predict the frame 4100. And we can see that at a prediction horizon of 1, we are very, the predictions that we can obtain are very good. So we can both forecast the onset of a laboratory earthquake, but even its space-time propagation. And the same thing can be observed regarding the predictions obtained at a prediction horizon of 2, at a prediction horizon of 3, and at a prediction horizon of 4. Well, if you look to the predictions obtained with a model trained to forecast the velocity field 5 frames in advance, we can see that in this case, the model is not capable nor to predict the onset of the laboratory earthquake, but neither its space-time propagation. So we can estimate that the maximum predictability horizon of the FOAMQUAKE experiment is of the order of 3-4 frames. And especially we can see even this result in this plot that represents the predicted versus true velocities for different prediction horizons. And we can see that as we increase the prediction horizons, the predicted velocities tend to be flattened. So we tend to underestimate the velocity field. And again, the same thing can be noticed in these subplots that instead represented the predicted magnitude versus the true magnitude, and even the predicted average leap versus the true average leap, and the predicted rupture area versus the true rupture areas for all the analog earthquakes generated by one FOAMQUAKE experiment. And we can see that a prediction horizon of 1, we can predict very well all the source space parameters of analog earthquakes. Well, if you increase the prediction horizons, these predictions became very bad, and the number of analog earthquakes that we can predict decreases a lot. So the percentage here reflects the number of good predictions that you can obtain. So without, I don't want to show the same result, the same plots for the Giacomo experiment, but I would like only to show you this plot, which is an equal representation to the one that I showed you before for the FOAMQUAKE experiment. And here we can see that the maximum predictability horizon that can be achieved with the Giacomo experiment is longer and is of the order of 6-7 frames. So let's conclude this part about laboratory earthquake forecasting. So all these conclusions have been published recently on a paper on GRL. So if you are interested, you can check out this article. So we introduced a novel spatiotemporal regression to forecast surface velocity field. Our method allows us to forecast the onset, magnitude, and propagation of analog earthquakes up to a temporal horizon of the order of the duration. We found that deep learning methods outperform standard machine learning, and especially the use of convolution neural network, recurrent neural networks, which are some networks that emphasize the spatiotemporal sequentiality of the input, is critical. We found that it's critical, the usage of this kind of algorithms. And regarding the future applications, our study in some way paves the way to the application of transfer learning from different analog experiments to the natural prototype. And especially the challenging evolution of this study is trying to use the same methods we have employed in the laboratory with natural data, trying, for example, to predict fast and/or slow earthquakes from genetic data. So let's go to the last part of the talk, which is gonna be very, very quick. So don't worry, just the last few minutes of the presentation, where I'm gonna talk here about something that I'm trying to do right now, working with real data, especially from the Cascadia subduction system. So given to the great analogy between the space-time rupture patterns generated by analog models in the laboratory and space-time rupture patterns observed for the Cascadia subduction system, we decided to try to work with the geodetic data from this subduction system, where we have the subduction of the Juan de Fuca plate beneath the North American plate. And we are trying to use, especially to forecast slow earthquakes. Why slow earthquakes? Because slow earthquakes are very frequent in time. So we have access to a long enough catalog of slow sleep events that can be used with machine learning. Because of course, with machine learning, when you are using machine learning, you need a lot of data to train your model. And so slow earthquakes, for example, can be a perfect data set to be treated with machine learning. But there are some problems when you try to work with GNNS data, with geodetic data, that make slow earthquakes forecast very difficult. And here I linked the 4 of the main problems that you have. So the first one lies in the fact that GNNS data suffers from the presence of data gaps and mixing station. And these data gaps can be associated, for example, to station inactivity or inconsistent daily measurements. The second problem is that the number of GNNS stations may evolve over time, because, for example, some new receivers can be installed, or some receivers can be temporarily unavailable. Third, GNNS data are very noisy. So with respect, for example, to laboratory data, the things are more complicated. You have to deal with the noise. And fourth, the GNNS time series are the results of the combination of several different signals that can be both tectonic related and non-tectonic related. So if you would like to forecast slow earthquakes, the first thing to do is, first of all, trying to isolate slow earthquake signal from a geodetic time series. So a geodetic time series can be described as a combination of several signals, of the combination especially of a linear trend, of some annual and seasonal components, of some steps that can be related to the occurrence of earthquakes, or even to some human-induced changes, and to some tectonic transits that, for example, can be related to the occurrence of slow earthquakes. So what we are trying right now to do is trying to isolate from GPS time series slow earthquakes by using a trajectory modeling, trying to remove the trend, the annual and seasonal component, and its steps. This way, what we would like to obtain is a time series where the tectonic transients should be isolated. And especially once the tectonic transients are isolated, the second thing to do is trying to remove the majority of noise that characterizes the given time series. And especially one attempt that we are trying to apply is trying to use a sort of hamping moving average filter and a moving linear fitting to remove the majority of noise, and obtaining at the same time a velocity in time series. So here I represented the example from a GPS station PG-C5, which is a station located close to the Vancouver Island along the Cascadia subduction system. And here I represented the result of all the processing things that I described you. And especially here, ideally, each vertical peak should represent a given slow earthquake. But there's a problem, there's a big problem, which lies in the fact that when you apply a filter to a given time series, whatever time series is it, you cause a temporal delay in the signal of interest. So to remove the noise, we are here applying these two different filters, and these filters cause a delay in the signal that we are trying to isolate. And this becomes a problem if you would like to apply this method in real time. So what we are doing right now is trying to build a better model that can be useful to denoise the majority of noise of a time series without causing a long time delay. And we're trying to achieve this goal by using deep learning, using GNNS data from all over the world. So let's go to the next steps of my work will be dedicated to trying to improve the analysis of this GPS time series by employing different methods and testing the effectiveness of the denoising method for real-time forecasting of slow earthquakes. And we would like to extend the deep learning approach not only with the geodetic data, but also using seismic data that can potentially improve the forecasting of slow earthquakes. Given that recently it has been demonstrated that there's a strong connection between the tremors measured along the Cascadia subduction margin and the signature of geodetic data observed at the surface of our planet. And also we would like to try to proceed even on the laboratory side, and especially we would like to test the applicability of the forecasting deep learning approaches that we have applied with the GeoQuake and FOAMQUAKE experiment with the other seismotectonic canal models of the megathrust seismic cycle. And we are also trying to develop an accelerometric network along the FOAMQUAKE experimental model. So take-home message, and I almost finished. So I hope that I convinced you that seismotectonic canal models are a very useful tool to investigate the long-term megathrust seismic behavior. And the peculiarity of producing a large number of analog seismic cycles allows us to use deep learning techniques with this kind of laboratory data that we can produce. And especially, I hope that I demonstrated you that spatiotemporal deep learning can be used to forecast analog earthquakes generated by different seismotectonic models. And we forecast these analog earthquakes up to a temporal horizon of the order of their durations. And this ability of deep learning to automatically extract and model some special features across multiple timescales in some way provides optimism that in the future, similar results may be achieved with the real data from natural subduction systems. And so I finish, and thank you so much for your attention. And if you have any questions, feel free to ask me.
Thank you very much, Giacomo. That was really interesting. Yeah, do we have any questions from anyone? You can just unmute and ask, or you can put it in the chat, or I guess I can start. So
yeah.
When you're doing your sort of deep learning on your analog models, did you do a different training data set for the ones with the asperities, like 2 asperities and one with 1, or is it all the same?
Yeah, so we treated the experiment separately, each experiment separately. So basically, what you do from one experiment, you split the input data set into training, validation, and testing set. So basically, the training set is different for each kind of experiment that we tested.
So does this mean, okay. Yeah.
Go.
Does it mean that your asperity always has to be in the same place for you to get the best prediction, or?
Yeah, this is a great question. This is a great question. Yeah, so we have tried to, for example, train one model based on one configuration and then test this artificial intelligence model with the data coming from an experiment with a different configuration.
Mm-hmm.
And it works. It doesn't work so well as of course in the case you're using always only the data from one experiment. This is due to the fact that you already told me now, which is due to the fact that it's very difficult to generalize with deep learning with this kind of deep learning architectures. So basically, if you train one model, for example, with data from a single asperity experiment, where you have always the raptor that is in the same location, of course, because you have only one seismogenic source, then it becomes quite difficult for the model to understand that, for example, if you test the model with data from a double asperity model, it becomes very hard for the model to understand if the next laboratory earthquake will be at a double asperity raptors.
Mm-hmm.
There are some methods to try to generalize more the results that you can obtain with one architecture, but basically it was not the main goal of our work. So the main goal was to propose a novel method, a spatiotemporal method, and we decided to mainly focalize our attention into the different predictions that you can obtain with different experiments. To test which was the easiest experiment to predict, and not try to build a very universal architecture, let's say.
Yeah, so I guess it might be pretty good for like repeating earthquakes in nature, and then
yeah, absolutely. Yeah, absolutely. And for example, one dream, let's say, about the future work will be try now to use these architectures with slow earthquakes. And of course, and one thing that we would like to try to do is, just a slide that show this thing. We would like to try to use transfer learning, no? You know, probably transfer learning, which means simply train a model based on a given data set. And in our case, this data set will be a laboratory data set. And then try to use this model with natural data. And of course, if you want to do this exercise, what you need to have a model that it's very good in generalized results. So for example, you can try to build a model using different experiments with a lot of different configuration, with one asperity, two asperities, three asperities in different locations, and then try to build a very general model.
Sounds great. Do we have any more questions?
That covered my question. I was just about to ask about the extending the model to natural earthquakes and if it was flexible enough to do that. I do have a more sort of technical question about the PIV.
Yeah, sure.
How did you decide the resolution for the PIV gridding, or like the grid increment? Because it's sort of arbitrary when you kind of process the PIV data, and I'm doing that myself, so I'm curious what you did.
Yeah, so you mean like some parameters like the overlapping, like the number, you know, of pixels that you can use in the cross correlation, things like that, you mean?
Exactly,
or you mean,
yeah.
Yeah, there's not, of course, a universal way of deciding these parameters. So what we did was simply to test different possibilities, and we compare. Even one thing that we did, we compared the results obtained with different configurations. Like, of course, like for example, the number of analog earthquakes you can identify with one particle image velocimetry, let's say, configuration, and another particle image velocimetry technique configuration. So to test the let's say impact on the results of the particle image velocimetry technique. But of
So
course so we simply test different configuration and we identified what was for us the best way to monitor the experiment. So
nice. Yeah, so I'm glad that I'm doing the same thing, just trial and error and try to extract what you're looking for.
Yeah. I think it's the only way that we have to identify the best configuration.
Cool, thanks.
Do we have any more questions?
I do have another question too. I was thinking about have you seen the biaxial experiments of McClaskey, that group, where they have a biaxial apparatus, so you have a little more spatial, you have a more of an idea of the spatial change across the fault. So I guess do you think you could apply these like methods to those experiments well?
Yeah, but which is the monitoring system that are they using? So they're using they're monitoring the experiments with acoustic emissions or with other kind of.
So they have acoustic emissions and then some, it's obviously not PIV the same, but
because when you are working with acoustic emissions, it's quite difficult to identify spatial patterns for several motivations. The first one is generally that you use only a few sensors, no? Yeah. So you to identify, for example, the propagation of analog raptors, you need to use a lot of sensors that are very precise, because of course you need to distinguish very small variations in terms of arrivals, of the first arrivals of the waves. So, and generally in the experiments, for example, to my knowledge, in the experiments that, for example, at La Sapienza, laboratory they are doing, or at the INGV, where they try to use machine learning, generally they always use data coming from only one or two sensors.
Okay.
So
you have to solve the location problem before you.
Yeah, you have to solve the locations problem, and then it's even the algorithms that now we are using with seismotectonic megathrust models. I'm not sure that they can work with acoustic emissions.
Okay.
They're totally different kind of data, So but I don't know, maybe they're improving their ability to monitor the experiments, so maybe in the future they will be able to even consider the spatial components of the processes.
Cool, thanks.
I guess I have one more quick question.
Go.
So I think it's pretty cool how you're using voice as your sort of asperities. So how come the voice created good asperities and the sand didn't? Was it just because of the shape, or was it something to do with like the strength of it? Or
you mean why in the sand you cannot nucleate earthquakes? No,
and you can in the ice. Yeah.
Okay, yeah, because this is due to there was a slide even for that. This is due to the properties of the materials that we are using, the frictional properties. So the rise is a velocity. So here, for example, these are results from velocity stepping test, these kind of experiments where you change the velocity and you measure the friction, the variation of the friction. And basically what you can obtain, you obtain what is called the A-B parameter, which is the rate parameter that describes let's say how one material change its friction due to a velocity perturbation. So a velocity weakening material is a material that after a velocity perturbation, the friction coefficient becomes slower. Okay, this case with respect to the previous state. So it's a material where you can nucleate instabilities, and this is a case of the rise. So here the A minus B is negative, and this is the results from the rise. While instead the sand has a velocity, a minus B parameter, which is almost 0, which means that there's no dependence of the friction on the velocity. So within the sand, if you, for example, ideally perform one experiment with only the sand above the analog megathrust, you will not create any instabilities. So you cannot accumulate stress at the contact between the foam rubber wedge and the sand. So there's there will be a sort of continuous creep. So within the sand, you don't nucleate any instabilities.
That's cool. It's interesting.
Yeah.
Okay, so that takes us to 3 o'clock. So yes, thank you once again, Giacomo, for a really great talk.
Yeah, thanks, Giacomo.
Guys. Thank you so much.